Call is now being recorded. Okay, once again, good afternoon, everyone. So in this section, we're going to study a specific function or a specific statistic. We call it as the likelihood function that can also be used to summarize data. So in definition 6.3.1, we have here the definition of a likelihood function. So we let f of our observed sample bold x given our parameter theta. Okay, theta here is unknown, but it is fixed. So denote the joint PDF or PMF of our sample, which is actually a IID, random sample, or the random variables x sub 1 up to x sub n. Then given that the sample bold x is equal to this x, small bold x, which is the realized value of our random sample, then the function of the parameter theta defined by L of theta given x, which is equal to our PDF f of x given theta is called the likelihood function. If we're going to look at our definition, the likelihood function here is somehow it seems that the likelihood function is the joint PDF or PMF of our random sample. Yet the likelihood function is actually a function of our unknown parameter theta, because the joint PDF per se here, no, the joint PDF per se, this is a function, no, it's a function of our observed sample small x given our parameter theta. So in our PDF, actually, we are considering theta as fixed, no, fixed but unknown, and then the observed sample bold small x as the variable. While in the likelihood function here, no, in the likelihood function, uh, the the this is a function of our parameter theta given our observed sample x. So our observed sample x is fixed, and then our theta, which is unknown, is actually varying uh, overall, no, varying overall possible parameter values. This is just this is the thing that I want to emphasize in our definition, that our likelihood function here is a function of theta, even though in our definition it is being equated to the PDF or the joint PDF. So this is called the likelihood function, no? This L. So if the sample is a discrete random vector, then the likelihood function of theta given x is equal to the probability that x is equal to the observed value small x given theta. So if we're going to compare the likelihood function at two parameter points, say theta sub 1 and then theta sub 2, say the probability that x, our sample, is equal to this observed sample small x given theta sub 1, by definition is equal to the likelihood function of theta sub 1 given x, and we assume to be greater than the likelihood function of theta sub 2 given x, and this is equal to the probability that x, no, the sample is equal to the observed sample x given theta sub 2, since we know that x is a discrete random vector. Because of this assumption, then we say that the sample we actually observe is more likely to have occurred if our theta is equal to theta sub 1 than if theta is equal to theta sub 2. So which can be interpreted as saying that theta sub 1 is more plausible value, or in other words, is more reasonable value for the true value of our unknown. It's an unknown parameter theta than is theta sub 2, due to our assumption that the likelihood function of theta sub 1 given x is greater than the likelihood function of theta sub 2 given x. So let's have an example to fit this definition. We have the negative binomial likelihood. So we let x have a negative binomial distribution with r is equal to 3, and then the success probability p. So if small x equals 2 is observed, then the likelihood function is a fifth degree polynomial on p, where the value of p is between 0 and 1 inclusive, defined by this. No? This is our likelihood function. The varying uh, expression here is p, the parameter p, and our sample, observed sample, is fixed, which is equal to 2. So we have this. And since our random variable is a discrete random variable, then it is equal to the probability that x equals 2 given the parameter small p. And then we have this. It's actually a combination of 4 taken 2. Our 4 here, nakuha yan siya on the PDF, no? Or rather on the PMF of our random variable x, having a negative binomial distribution, where x here refers to the number of failures before the R success. So itong 4 na to dito is actually parang ito yung formula natin. No? If x has a negative binomial distribution, okay, say with parameter rp, okay, x here refers to the number of failures before the R success. So the PDF for this, or the PMF rather, we have R and P. We have here a combination of R plus X minus 1 taken X. So we have here the probability of success raised to R, and then 1 minus P raised to the 1 minus P raised to X. And then the value of X, the support for this random variable, we have 0, 1, and so on and so forth. So in this case, 4, so we have R is 3, 3 plus 2 minus 1. So that is 4, and then this is our X value, which is equal to 2. And then 3 here is R, and then 1 minus P raised to 2. Okay, so this is the likelihood function is a fifth degree polynomial on our parameter P. If we're going to look at our equation here, obviously it is a function of our parameter P. Okay, ito, it's a function of our parameter P. So in general, if x is equal to small x is observed, then the likelihood function is a polynomial of degree, okay, it's degree 3 plus x. So we have here 3 plus, if we're going to expand 1 minus p raised to x here, the highest degree is actually x. So we have of degree 3 plus x. So this is the likelihood function, which is a function of our parameter p. Okay, so illustration lang yan siya sa ating definition. So the likelihood principle specifies how the likelihood function should be used as a data reduction device. We have here the likelihood principle that if bold small x and bold small y are two sample points, such that the likelihood of theta given this sample point bold x is proportional to the likelihood function of our parameter theta given the sample point y, proportional. Take note of that. That is, there exists a constant C of these sample points x, y, such that we could express the likelihood function of theta given x as the product of this constant C of x, y times the likelihood function of theta given y. That is for all theta. Then, according to the likelihood principle, then the conclusions drawn from x and y should be identical. Or we could say the conclusions drawn from x and y should be the same. Okay, we have a note here that our constant c of xy may be different for different pairs, no, xy pairs. But the c of xy does not depend on our parameter theta. So we have a special case. If we're going to consider the constant to be equal to 1, so the likelihood principle states that if two sample points result in the same likelihood function, then they contain the same information about theta. That is why I've said a while ago, the x and y, the information or the conclusions that we draw should be identical or it could be the same. In the case, no, when c is equal to 1, then we have same information about our parameter theta. It states that even if two sample points have only proportional likelihoods, then they contain equivalent information about theta. So the rationale is this: the likelihood function is used to compare the plausibility of various parameter values. Say we have two parameter values, theta sub 1 and then theta sub 2, and if the likelihood function of theta sub 2 given x is twice the likelihood function of theta sub 1 given x, then in some sense, our parameter theta sub 2 is twice as plausible or reasonable, no, as theta sub 1. But if equation 6.3.1 is also true, then we could have this equality that the likelihood function of theta sub 2 given y will also be equal to twice the likelihood function of theta sub 1 given y. Thus, whether we observe the sample point x or the sample point y, we conclude that theta sub 2 is twice as reasonable or plausible as theta sub 1. Okay, so ito yung sa ating likelihood principle. So one form of inference in which the likelihood can be used is the fiducial inference. Okay, this fiducial inference sometimes interprets the likelihoods as probabilities for theta. Okay, that is, the likelihood function of theta given x is multiplied by m of x, which is a function of x, and then the product of the product of m of x and the likelihood function is interpreted as the PDF for theta. Take note, no? Ito yung PDF for our parameter theta. Because the PDF, the function f of x given theta is actually the PDF of our sample. The likelihood function is not necessarily the PDF of our parameter. So in this case, now in this, the PDF of our parameter is actually the product of m of x and the likelihood function of theta given x. Let's have an example. We have the normal fiducial distribution. Say we let x sub 1 up to x sub n be IID, normally distributed with mean mu and variance sigma square, where sigma square or the variance is known. So the only unknown parameter here is the mean, population mean mu. And then using the expression 6.2.4, since we equate our likelihood function, no? Itong likelihood function natin, mu given the observed sample point x, ito yung nakasulat, it is equal to this PDF. Ito yun. We have 2 pi sigma square. Sulat ko na lang dito. We have negative n over 2. We have here the exponential of the negative summation of x sub I minus x sample mean square I from 1 up to n divided by 2 sigma square, and then times the exponential function of negative n. We have x bar minus mu quantity square divided by 2 sigma square. Okay, ito yung expression sa 6.2.4. So we first note that equation 6.3.1 is satisfied if and only if this sample mean x bar is equal to the sample mean y bar, and in which case, using our 6.3.1, the constant c of xy is equal to this expression. So if we're going to verify that, we have here the c of this two sample points xy based on our equation 6.3.1 above, yan, no? Proportional yung kanilang mga likelihoods, then we can have this ratio for our constant. 2 pi sigma square negative n over 2, okay? Summation I from 1 up to n. Then we have xi minus x bar quantity square over 2 sigma square exponential negative n x bar minus mu quantity square over 2 sigma square. You divide it by the likelihood function of our parameter theta or parameter mu given another sample y. So, pareho lang naman. The exponential, but in this case, we have the summation of y sub I minus y bar square over 2 sigma square. I from 1 up to n. We have here the exponential of negative n. We have here y bar minus mu square over 2 sigma square. Okay? So, this one would cancel out. And this would be equal to the above. No? Above expression. Ito, sa above expression, the exponential of the negative summation of xi minus x bar quantity square over 2 sigma square I from 1 up to n plus, okay, summation of yi minus y bar quantity square over 2 sigma square I from 1 up to n if and only if, no, if and only if the sample mean x bar is equal to the sample mean y bar. So if that will happen, if this is true, okay, if this is true, then we can cancel this out. Yan, no? 1 yan siya. So that's the result. Kung ilagay natin itong exponential function sa itaas, now applying na, say we have here e to the a, e to the b, then we have here e to the a minus b. Okay, so we have that result for our constant c of x, y. Okay, yan yung nakasulat dyan. Using the expression 6.2.4 for our likelihood, equating it to the PDF, and then equation 6.3.1, in which the likelihood function, no, the two likelihood functions are proportional, is satisfied if and only if the sample mean x bar is equal to y bar. Okay, so yan yung verification. Thus, the likelihood principle states that the same conclusion about our unknown parameter mu should be drawn for any two sample points satisfying x bar is equal to y bar. In order to compute for the fiducial, okay, the PDF for our parameter mu, so we define m of x, which is a function of x, to be equal to n to the n over 2. Then we have here the exponential of this expression. Then the product, m of x, and the likelihood function of u given x will be the PDF for our parameter mu. And in this case, it has a normal distribution with mean x bar and variance sigma square over n. So this is the fiducial distribution of mu, and a fiducialist can make the following probability calculation regarding mu. Paano natin nakuha yan? Say we have here our likelihood function, say product, no? Ang product natin. Say m of x, and then the likelihood function of mu given the sample x. So yung ating m of x given n to the n over 2, the exponential summation I from 1 up to n. Then we have here x sub I minus x bar quantity square over 2 sigma square. Okay? Ito yun. That's for our m of x and our likelihood function. Okay? Yung ating likelihood function, what do we have? We have 2 pi sigma square raised to negative n over 2. We have here the exponential of the negative. We have the summation of x sub I minus x bar quantity square over 2 sigma square I from 1 up to n. Okay? And then times the exponential. We have negative n. We have x bar minus mu quantity square over 2 sigma square. Okay? So, ito, their product is equal to 1. Okay? Yung product niyan is equal to 1. And then, we have itong product nitong mga n natin. So, we have here n over 2 pi sigma square. Pareho lang naman yung nila. Raised to n over 2. And then we have here the exponential. Okay. Ano yung iwan na lang? Negative n. Take note, no? Yung parameter, yung variable natin dito is actually the mu. Fix ang ating sample. So we have the x bar. We can now interchange mu minus x bar. Quantity square divided by 2 sigma square. Or we can write it, we can write it as 1 over 2 pi sigma square over n. Okay, this is raised to n over 2. And then we have here the exponential of negative of mu minus x bar square divided by 2 sigma square over n. Okay, so this implies na ito yung fiducial PDF of our parameter mu. So this implies that m of this sample x times the likelihood function of mu given x. This is as a function. This is a function, no? As a function of our parameter mu. It has, now according to this, it has a normal distribution with mean. What is the mean of that? X bar, and with variance sigma square over n. PDF. Okay, so satisfy nito. It has a normal distribution with mean x bar, and the variance is sigma square over n. So the parameter mu, okay, the parameter mu has a normal distribution with mean x bar and variance sigma square over n. Hence, mu minus x bar. In other words, we standardized mu here. No, we standardized mu here. Mu minus its mean, which is x bar, divided by the standard deviation. So kaya yung standard deviation niya, sigma over square root of n. We standardize the mu here, so it has a normal distribution with mean 0 and variance 1 distribution. Thus, we can have this no? Result, diretso na tayo, because this is true, because we can take this as z, no? We can take this as variable z, or random variable z. Okay, so parang z ito. Okay, the probability that our random variable z is greater than negative 1.96 but less than 1.96. Actually, we consider alpha here to be equal to 0.05. And then this would imply that our alpha over 2 is equal to 0.025. And then the 1 minus alpha, which is 1 minus 0.025, we have here 0.95. And the value n or z of 0.025. No, the upper percentile point of the normal distribution here is equal to 1.96. So we can have this equation now, no? That 0.95 is equal to the probability that z is greater than negative 1.96 but less than 1.96. So simplifying what is inside the parenthesis, then we have this results. Okay, and then we have here third result, the probability that our parameter mu is greater than this expression x bar minus 1.96 sigma over square root of n, but less than x bar plus 1.96 sigma over square root of n. So the likelihood function here is being used for us to be able to determine the PDF of our unknown parameter mu. Nalaman natin yung PDF ng ating or the probability density function for our unknown parameter mu. It has this distribution, or nalaman natin yung distribution ng ating parameter mu. Okay, so that's one of the application of the likelihood function as a data reduction technique. So reading assignment, you read section 6.3.2. We have the formal likelihood principle. Okay, this is a reading assignment. So let's proceed to the last data reduction technique. What we have, we call it as the equivariance principle. So the previous two sections both describe data reduction principles in the following way. So we have the function of the sample, t of x is specified, and the principle states that if the sample points x and y with a condition that t of x is equal to t of y, then the same inference about the unknown parameter theta should be made whether the sample point x or y is observed. So if the function, supposedly it should be t of, this is big of the sample, because a sufficient statistic is a function of the sample. So it should be t of big X is a sufficient statistic when sufficiency principle is being used. Now, given this condition, I think you can still remember yung ating theorem in the sufficiency principle. Saan yung notes ko? Kalimutan ko. Yung hindi ko nakita yung isang pa. We have that condition uh, that two no realized values given our function, they are equal. Uh, so our t of x here is the sufficient statistic. Recall that a sufficient statistic captures all the information about our parameter in the given sample. So the value of t of x is the set of all likelihood functions proportional to the likelihood function of theta given x if the likelihood principle is being used. Ganun din. Sa example natin kanina dito, we have this condition, yung sa example natin that the sample mean x bar is equal to the sample mean y bar. Yun nakita niya based on our example kanina dito. X bar here. Okay, the realized value. And then let's go to the equivariance principle. It describes a data reduction technique in a slightly different way. So in any application of the equivariance principle, the function t of x is specified. But if t of x is equal to t of y, then the equivariance principle states that the inference made if x is observed should have a certain relationship to the inference made if y is observed. Yung sa sufficiency principle at saka sa likelihood principle, they have the same inference. Whether we're going to use the sample point x or the sample point y. But for the equivariance principle, the inference made if x is being observed should have, says here, it should have a certain relationship to the inference made if y is observed, although the two inferences may not be the same. This restriction of the inference procedure sometimes lead to simpler analysis, just as do the data reduction principle discussed in the earlier section. Okay, so although commonly combined into what is called the equivariance principle, the data reduction technique, uh, the data reduction technique we will now describe actually combines two different equivariance considerations. So the first one, we have the measurement equivariance. It says that the inference made should not depend on the measurement scale that is used. It should not depend. So for example, suppose two foresters are going to estimate the average diameter of trees in a forest. The first forester uses data on tree diameters expressed in inches, and the second uses the same data expressed in meters. Now both are asked to produce an estimate in inches. Now in inches. So the second forester might conveniently estimate the average diameter in meters and then transform the estimate to inches. So if you're going to transform it into inches, obviously, measurement equivariance requires that both foresters produce the same estimates. Okay, that's the first type of equivariance. The second type of equivariance, actually an invariance, it is called a formal invariance. So it states that if two inference problems have the same formal structure in terms of the mathematical model used, then the same inference procedure should be used in both problems. So ano yung mga elements natin so that the inference problems have the same formal structure? So they must have the same parameter space, that is big no big theta, the same set of PDFs or PMFs for the sample we have here, and then the same set of allowable inferences and consequences of wrong inferences. Kasali nandito yung same, no? Same, we will say it's the same type of error committed for our uh, or the type of same type of error being committed. Consequences of wrong inferences. So we have three, no? Three elements of the model that must be the same. So ito ngayon yung equivariance principle. If y is equal to g of x, is a change of measurement scale such that the model for y has the same formal structure as the model for x. So that means it satisfies all the three elements. Then an inference procedure should be both measurement equivariant and formally equivariant or formally invariant. Okay, let's have an example to illustrate these two concepts of equivariance. So we have the binomial equivariance. Let X have a binomial distribution with a sample size n. This is actually the number of trials known, and then the success probability p unknown. Okay? Unknown yung ating parameter p. So x here refers to the number of successes. So p is the probability of success, which is unknown. So estimate natin itong unknown na probability of success. So let t of the sample be the estimate of p that is used when the random variable x is equal to its realized value, small x. So instead of using the number of successes to estimate the probability of success p, why not to make an inference about p? Why not use the number of failures? Y, we have here, we can now express now y. We have this transformation for x. Y is equal to n minus x. And we can show easily that y also has a binomial distribution with parameters. So the same number of trials, n, which is known, but the probability of success here, if we consider y here, y as the number of successes, so ang probability of success niya is the q, which is equal to 1 minus p. So if we let p star of y be the estimate of this q parameter that is being used when y is observed, y is equal to y is observed. Okay, so that would imply now, kung ito siya, estimate ito ng q, so it would imply that 1 minus t star of y will be an estimate of our parameter p when y, random variable y is equal to y, is observed. So ito na ngayon, ito would estimate our parameter p when y is equal to y is observed. If x successes are observed, then the estimate of our probability of success p here is t of x. Diretso naman. So yung estimate ng p is t of x. So if there are x successes, then there are n minus x failures. Okay, take note, n minus x failures. So 1 minus t star of n minus x, because this is a failure, and then t star is a function for y. So we have t star of n minus x is also an estimate of our parameter p. Again, no? So measurement equivariance requires that these two estimates be equal according to our measurement equivariance. So t of x is equal to 1 minus t star of n minus x. Okay, since the change from x to y is just a change of measurement scale, then furthermore, for formal structures of the inference problems based on x and y are the same. They are the same. They have the same parameter space. No? Yung parameter space natin dyan, the value of p is between 0 and 1. The same parameter space. Yung p at saka q is between 0 and 1. Inclusive. Okay? Pareho ba yung kanilang kan? Pareho ba yung kanilang set of PDFs or PMF? In this case, yes. Because x has a binomial distribution, y also has a binomial distribution. Yan. X and y both have a binomial and theta distribution. So the theta here could refer either to p when we consider x, no? When we consider x, and then theta is equal to q when we consider y. So formal invariance requires that t of z is equal to t star of z for all z uh, on the support of our binomial distribution from 0 to n. Thus, measurement and formal invariance together require that t of x, etong part na to dito, t of x is equal to 1 minus t star n minus x. We apply here the measurement equivariance. Measurement equivariance. Equivariance. And then the next equality here, we apply the formal, okay, invariance. So this would further imply, okay, this would further imply that t of our observed sample x will be equal to 1 minus t of n minus x. So we have that. So the question now, how does equivariance principle applies as a data reduction in this problem? Now, how does equivariance principle applies as a data reduction for this given problem? If we do not know, take note, no? If we do not know that t of x is equal to 1 minus t of x, then we're going to determine, no? We're going to specify all the, no? All these values. We should have to specify t of 0, t of 1, up to t of n. If we do not know this, no? Ito naka-highlight dito. That t of x is equal to 1 minus t of n minus x. Dapat alamin natin kung ano yung t of 0, t of 1, up to t of n. Pero kung alam na natin ito, that t of x is equal to 1 minus t of n minus x due to the equivariance principle. So ang hahanapin na lang natin, we're going to specify only t of 0, t of 1, up to t of n over 2, where this function here refers to the greatest integer not larger than n over 2. Bakit ito na lang yung hahanapin natin? Say for example, makukuha na natin yung value ng t of n kasi alam na natin to, t of 0. So we have only 1 minus t of 0. And then we can also determine also the value of t of n minus 1 because we know already the value of t of 1. So instead of specifying all these n values, eto na lang, kokonti na lang. Because we applied equivariance principle in our problem. And we arrived at this, no, at this equality. So this is the type of data reduction that is always achieved by the equivariance principle. Okay, so any questions or clarifications dito sa equivariance principle? A key to equivariance argument in example 6.4.1 and to any equivariance argument is the choice of transformations. So the data transformation used in example 6.4.1 is y is equal to n minus x. So the transformations, changes of measurement scale used in any application of the equivariance principle are described by a set of functions on a sample space called the group of transformations. Okay, so meron tayong group of transformation that we're going to use when we're going to apply the equivariance principle. So we have here the definition for a group of transformations, a set of functions, uh, which is the set containing g of x, such that g is an element of script. From the sample space, script x onto script x is called a group of transformation of script x if the three conditions are satisfied. 1i, we have the inverse for every g in the set script g. There is a g prime of an element of script g such that g prime times or g prime composition g of x will be equal to x for all x in our sample space script x. And then secondly, the composition for every g element of script g, and then g prime element of g script g, then there exists a g double prime. No, take note, this is an element, still an element of script g, such that this composition g prime of g of x is equal to g double prime of x for all sample point x in our sample space script x. And then we have the last requirement, the identity. The identity E of x defined by, so E of x is equal to x as an element. Okay, this is a function, so this is an element of script g. So as is stated as part of the definition of a group, but 3i is a consequence of 1i and 2i and need not be verified separately. It's actually an exercise, no, in 6.38. Take note, we have here an ontoness property of our function. In other words, we have here g, which is a function from the sample space script x to script x, okay? And it is onto. This function is onto. So anong ibig sabihin ng onto? Function is onto. Diba? When you say a function, meron tayong domain at saka codomain. If the range of the function is equal to its codomain, and the range of the function is equal to the codomain, then our function is onto. So mathematically, pwede natin isulat yan na for all, sabihin natin, for all y, element of the sample space script x, dito yan, dito yung y. So for all, dapat lahat. Kasi yung range equal sa codomain. So for all y in the script x, there exists an x element of the domain. Yan, dito yung small x, domain, such that yung image ng x under G should be equal to y. Yan yung gagamitin natin to show that our function is onto. So kung merong problem showing that a given set of functions is a group of transformations, be sure first that your functions in that set onto siya before verifying the three requirements: inverse, composition, and then identity. So let's have an example. Continuation of example 6.4.1. For this problem, only two transformations are involved. So we have a set script G containing G sub 1 and G sub 2 with G sub 1 of x is equal to n minus x and G sub 2 of x is equal to x. Is script G a group of transformations? Hindi naman ito napakita sa libro. But I'm going to show you how in order for me to illustrate the definition. Okay, so solution to that. Showing that script G is a group of transformation. So sabihin na lang natin, onto muna. Kasi hindi natin alam kung onto ba yung G sub 1 o onto ba yung G sub 2 na function. Okay? So para dito, yung G sub 1 natin, it's a function from the sample space to the sample space. So in this case, itong sample space natin dito, script x is actually the set 0, 1. Yes? Meron question?
This one. So for question, you have 4 minutes.
Ryan?
We'll be checking your attendance. So I'll just calling the list of students who are present today, just making sure that they are really in front of their computer listening to the discussion. Alexandra Hibaya.
I think
are you around?
Okay, sir. Mute ko lang, try ko lang mute si Ryan.
Althea?
Ma-mute ko si Rhea.
Okay, Althea is present.
Okay, so okay, we have that. We're going to show that our G sub 1 function and G sub 2 is onto. So it's a function from the same, no? The codomain and the domain are the same. So in this case, our domain here, yan yung support ng ating function, di ba? Y is equal to n minus x, di ba? G sub 1 is capital Y, or Y is equal to n of x. So yung Y binomial, so the support of that is from 0, 1 up to n. Same thing with G sub 2. So yung script x dyan is from 0, 1 up to n. So yung onto, no? The ontoness I'm going to show. So G sub 1 is onto. Bakit onto yung G sub 1? G sub 1 is onto. Why? Because or since for all y, dito meron tayong y dyan. For all y, lahat, dapat yung sa codomain range. For all y, element of our this, no? A sample space. Alaman natin yung value ng y should be numbers from 0, 1 up to n because y refers to the number of failures, no? Sabihin natin the number of failure, and then x refers to the number of successes. Okay, so we have that for all y, element of that. We are sure that there exists an x in our sample space. Ito ngayon, it refers to the domain, sample space, such that, I hope na alam niyo yung formula natin, such that yung mga notation natin, g sub 1 of x here is equal to y. So onto, klaro, lahat naman. Merong nag-a-appear dyan na x. Kunwari ang x ni mo 0, ano yung y? Kung x0, ano yung y? N. Kung x1, ano yung y? N minus 1. Okay, so there exists an x such that yung g sub 1 of x is equal to y. Also, g sub 2 is onto, klaro naman ito. Kon ko lang, no? In-emphasize ko lang. For all y, g of 2 naman, palitan na natin yung no? Element of this given sample space. So there's still an x here, element from 0, 1, up to n, such that yung g sub 2 of x is equal to y. Pareho lang naman. So in this case, yung y natin dito is actually equal to x. Dito, kulang yung space natin. No? Dito yung y is equal to n minus x. Okay, ito. N minus x. Andito yung y dito, equal siya to x. So g of 2 is equal to x. So kung y natin 0, no? Y natin 0, then there exists an x which is also 0, such that g of 0 is equal to 0. Okay, on to this. Next, inverse. Are going to show na nag-exist yung inverse. Take note, no? For every g, there should be a g prime in script g. Ano kaya itong g prime ng g1? So we have this g1 of g1 of x. Ano yung g1 of x? g1 of n minus x. Okay? Ito yung n minus x. So g1 of n minus x, this is equal to n minus n minus x. And this is equal to x. So it satisfies. This is true for all x. So the inverse of g1, and g1 inverse is equal to g1. Okay, nag-exist. What about sa g2? g2 of g2 of x. So we have here g2. What is g2 of x? X. Okay? And then what is g2 of x? X. So, ano implication nito? So the inverse of g sub 2, so g sub 2 prime, will just be equal to g sub 2. Nag-exist. That's the second, not the first. And then next, we have the composition. Composition. Take note, balik tayo. For every g, and then g prime, then there exists a g double prime, which is also an element of g. Yung composition ng g at saka g prime is merong lalabas na function g double prime, which is also an element of script g, such that this will say satisfied. Okay, balik tayo. Marami ito, no? Sa case na pwede sabihin natin. Una, say g1 of g1 of x. Okay, alam na natin ito na equal to x, no? Equal to x. Pero itong x is equal to G sub 2 of X. So yung composition nitong dalawa, G1, G1, is G2, which is also an element of script G, no? Where we know that G sub 2 is an element of script G. Next, G1, G2 of X. So this is equal to G1 X. Pero ano yung G1 of X? N minus X. Pero ano yung N minus X? Yung N minus X is actually equal to G1, no, of X. So, yung composition nitong dalawa, G1 and G2, is G1, where G1 is an element of script G. Okay? Dito naman, G2, G1 of X. Okay? So, pwede natin hanapin yan. So, we have here G2 n minus X. So, ano itong G2 of n minus X? N minus X. And this is equal to G1. Okay? G1 of X. Again, your G1 is an element of script G. G2 of G2 of X. Okay, alam na natin yan sa itaas, equals to X. So yung X natin is G2 of X. Again, totoo na yung composition ng mga functions will lead to a function which is also in script G. So composition property is satisfied. What about the identity? Identity property. So yung identity property for this, okay, sabihin natin the identity element of our script G here is G2. Okay, since we know that G2 of X is equal to X. So yung G2 element ng script G. Therefore, script G is a group of transformations. Any questions or clarifications? Kung may book kayo dyan, hindi naman ito pinakita, no? We have just the definition and then of being a group of transformations. Walang question? So let me proceed. Parang walang question yata. So to use the equivariance principle, we must be able to apply formal invariance to the transform problem. That is, after changing the measurement scale, we must still have the same formal structure. As the structure does not change, we want the underlying model or family of the distributions to be invariant. So this requirement is summarized in the next definition. So we let script F be the set of all PDFs or PMFs for our sample X, and let script G be a group of transformations on the sample space as script X. Then script F is invariant under the group script G if, no, for every theta element in the parameter space a big theta and G element of the group of transformation script G, then there exists, no, there exists a unique theta prime element of the parameter space theta such that y is equal to g of x has a distribution f of y given theta prime, and then x has a distribution f of x given theta. Okay, so let's have an example to this definition. So in the binomial problem that we have, for both G1 and G2, if X has a binomial distribution with n number of trials, and the probability of success is p. And then if you have this transformation, that g sub 1 of x, we take that actually as y, no? N minus x. So this n minus x has a binomial distribution. It has a binomial distribution with n number of trials, and the probability of success is 1 minus p. So dito, sa problem na to, yung theta natin, itong theta na to, is the p. Okay? Is the p. Then there exists a unique theta prime. So in this case, the theta prime is equal to 1 minus p. So yung distribution ng x, ito yung theta niya. Okay, ito yung theta niya. Actually refers to this. And then the distribution of the transformation y, which is equal to g of x. Ito yung kanyang theta prime. Kaya theta prime siya dito, 1 minus p. Okay? So sabi dyan, also g sub, okay, so the p prime is 1 minus p, where p plays the role of theta in definition 6.4.4. So if we're going to consider our function g sub 2 of x is equal to x, now this transformation, so x having a binomial distribution, np, so p prime, np, kasi x pa rin siya, pareho lang naman, so p prime is also p in this case. So thus, the set of binomial PMFs is invariant under the group script G, containing the functions G sub 1 and then G sub 2. Okay, so a simple example to our definition. But we have another example here. Example 6.4.6. Now the group of transformation is an infinite set. It's an infinite set. Then after that, we're going to verify that this group of transformations is indeed a group if it satisfies the three properties. We have the inverse, the existence of the inverse, na dapat kung meron kang function g in script G, dapat nag-exist yung kanyang inverse. That is also an element in script G. And then yung composition ng mga functions in script G, yung result ng composition must also be a function in script G. And at the same time, the identity function must also be an element of script G. So kung titingnan natin dito yung script G here, this is an infinite set because it is conditioned on the value of A, where A is any real number. So this set is an infinite set. But we're going to verify that this set of functions is indeed a group. So sabi dito, conditions 1 and 2 must be verified. So for 1i, nag-exist ba yung inverse? The inverse? Ano yung inverse ng g of a? If g of a is an element of script G, ano yung inverse ng g of a? Ito ngayon. So yung inverse ng g of a is the g of negative a. Kasi makikita natin dito, g of negative a and g of sub a of this. Ito yung sa g of a. Ito yung results. And then pag-apply natin ng g sub negative a, in other words, mag-plus tayo ng negative a. So kaya ito yung results. Ito yung result niya. And then simplifying, then we have here this sample having the realized values x sub 1 up to x sub n. So identity, no, ang result niya is the same. So the inverse of g of a is G sub negative A. Ayan. The inverse, G prime, is equal to G sub negative A. What about the composition? Pwede naman baliktad, no? Pwede magkabaliktad, pwede din hindi. Ito, G sub A sub 2, G sub A sub 1. So, itong una, itong green, ito, pag-evaluate natin yan, based on our assumption here, defined by that, no? G sub A of x1, x2. So, ito yung result. And then G sub A2 of this, realized values, then we have this. Ito yung results. And then pwede natin ito mag-group. Yan, mag-group natin yan. So that would be equal to G of A1 plus A2. Obviously, this, itong G sub A1 plus A2, is an element of script G. Bakit siya element ng script G? Guys, bakit element siya ng script G? Because A1 plus A2 is a real number. Yung value niya is between negative infinity to and positive infinity. Tama po ba? Because of this condition, palitan natin yung A ng A1 plus A2. That is still a real number. If A sub 1 is a real number, if A sub 2 is also a real number, then the sum is also a real number. And that is why G of A sub 1, A sub 2 is an element of script G. Hindi dito naka-reflect yung kanyang identity. If I'm going to ask you, what is the identity element of our script G? Anybody? Guys? May sagot ba dyan kung ano yung identity element ng script G natin? Hello? Kung hanapin natin yung identity element, in this case, yung G sub 0 x is the identity element. Elements of script G. Totoo naman yan. Kasi, sabihin natin, G of 0 of x or G of 0 of x1 up to xn. Yung pagka-define natin sa G, so that is x sub 1 plus 0 dot x sub n plus 0. And this is the same as x sub 1, x sub n. So the identity element of our set script G here is G sub 0. So satisfied lahat yung ating requirement, no, above in this definition 6.4.2. Okay, so the set script F. Now the set script F in this problem is the set of all densities. Now we have here densities F of the sample point given our parameters mu and sigma square for this random sample defined by this IID. Now normally distributed with mean mu and variance sigma square for some mu, any real number, and then sigma square to be positive. And then for any A, where A is any real number, then the random variable Y, yun yung ngayon natin kuhan. Random variable Y equal to Y sub 1, X plus 1, X sub 1 plus A. Y sub n here is X sub n plus A. So that's the G sub A of n. We'll have also a IID, normally distributed with mean. So ang mean niya ngayon is mu plus A, and the variance is sigma square. We know that the variance is given sigma square. So yung mean niya is mu plus A. So that's the joint distribution of Y. Okay. G sub A of X is in script F. Is in script F. The joint is in script F. Because the script F is the set of all joint densities. And hence, script F is invariant under the group of transformations script G. So if we're going to look at our definition 6.4.4, kung yung random variable X natin, normally distributed, rather random sample natin, IID, normally distributed with mean mu and sigma square. Etong Y natin, okay, the random sample na Y, random sample containing Y1, Y2, Y up to Yn, it has a normal distribution with mean. Ang mean niya is mu plus A and the same variance. So according to our definition, theta naman yun sa definition natin, theta and then theta prime. So in this case, yung theta natin sa X, yung theta natin sa X is simply equal to mu. Yung theta prime sa Y, sa transformation ng Y, is equal to mu plus A. Although, constant naman itong sigma square. Nakasulat naman dun na sigma square. Both unknown pala. Sorry. Both unknown. So, if they are both unknown, so, dapat palangan. Akala ko known. Yung kanina, unknown yun. Ano yung known? Saan yung problem? Kalimutan ko pala. So, both unknown. So, that's why we have here. Okay, so, elaborate lang yung example natin sa equivariance principle natin na instead of specifying all the values of our function t of the values in our sample space, t of 0, t of 1, up to t sub m, n. So hanggang kon lang, t sub 0 hanggang t sub n divided by 2. Because the other values for our function t is being specified since we know that our problem, we have shown that the equivariance principle can be applied for the problem. Yung nakuha natin sa equivariance principle dito sa problem na to, na itong part na to, okay, so any questions or clarifications? Ito yung last part ng chapter 6. So after that, we're going to proceed to chapter 7. That is actually point estimation. So yung sa chapter 6, we have the data reduction techniques. We have the sufficiency principle. We have the likelihood principle. And then we have the equivariance principle. Any questions or clarifications? Okay, thank you, Ryan. So anong coverage natin for this subject? For this subject, point estimation, we have also the interval estimation, and then we have also the hypothesis testing. Yun naman sa statistical inference. Okay, so let me proceed. Still have 6 minutes. Okay, point estimation. So this chapter is divided into two parts. The first part, we're going to know the methods of finding estimators. And then second part, we are going to evaluate these estimators. And then we're going to choose the best estimator. So the rationale behind point estimation is quite simple. So when sampling is from a population described by PDF or PMF, f of x given theta, take note, for our PMF, theta is unknown but fixed, and then x is varying on our sample space, no, on the support of. So knowledge of theta yields knowledge of the entire population. So hence, it is natural to seek a method of finding a good estimator of the point theta. And also, we're going to find a good estimator for a function of theta denoted by tau of theta. Pwede yan. Pwede din ganun yung interest natin. So, these methods described in this chapter can also be used to obtain estimators for a function of our parameter theta. The definition, first definition, a point estimator is any function of the sample. So a point estimator is actually a statistic. We have defined that in chapter 6. So that is any statistic is a point estimator because a statistic is a function of the sample and does not no does not contain any parameter. So there is one distinction must be made clear, the difference between an estimate and an estimator. So an estimator is a function of the sample, while an estimate is a realized value of our estimator. So there's a number obtained from our sample. So we have here a notation, the sample is taken, an estimator of the function. As an estimator is a function of the random variables, while an estimate is a function of the realized values, small x sub 1 up to x sub n. And then we have here the methods of finding estimators. Okay, the first one, we have the method of moments. Okay, so let x sub 1 up to x sub n be a sample from the population with PDF or PMF. Given this number of parameters, x sub 1 up to x sub k, so the method of moments estimators are found by equating the first k sample moments to their corresponding k population moments. So ito yung ating sample moments denoted by M1, M2 up to M sub k. So this is the kth sample moment. Ito. And then equate that to our population moments. So this is the first population moment, and this is the kth population moment. And we have here the corresponding equation for our, or the, the equation for sample moments and the population moment. So ito lang yung gagamitin natin in general. So the population moment, mu sub j prime, will typically be a function of our parameter, theta sub 1 up to theta sub k. So we can simply have this, no, mu sub j prime of the parameters. So the method of moments estimators, meron siyang notation dito sa book ni Casella and Berger. Yung estimator niya, tilde siya. So the estimator of method of moments estimator of theta sub 1, ito yung theta sub 1 tilde. Hindi siya hot. Pag tilde, that would refer to the method of moments estimator. So theta sub k, yung estimator niya, method of moments estimator, theta sub k tilde. So it's obtained by solving the system of equations for our parameter theta 1 up to theta sub k in terms of the sample moments. Okay, so let's have an example. Ito lang, isa lang, no? Before we go, normal method of moments in this case, no? So suppose x sub 1 up to x sub n are ID, normally distributed with mean theta and variance sigma square. In the preceding notation, okay? In the preceding notation, if we want to determine what is our m sub 1, so yung m sub 1 natin, according to our definition, no, yung m sub 1 natin is equal to x bar. Dahil dito, no, m sub 1, gamitin natin yon. That's 1 over n, the summation of uh, x sub I 1. Itong part na to. Ito sa m sub k. Ito sa last na nag-box ako. 1 over n. Okay, so this is equal to the sample mean x bar. Yung m sub 2 natin, m sub 2, according to our definition, 1 over n, the summation of x sub I square, I from 1 up to. Okay, ito yun. Okay, yung m sub 2. What about the population movement? Ito yung gagamitin natin for the population movement. Ito. It's the expectation. So ano yung mu sub 1 prime? So ito, mu sub 1 prime is equal to theta because mu of, okay, so, sorry. Here, mu sub 1 prime, according to our definition, is the expectation of x to the 1. And since we know that we have a random sample, IID, normally distributed, so the mean of x is equal to theta. So satisfy ito. What about mu sub 2 prime? So that's the expectation of x squared. According to our definition, ito, naka-shade no, sa itaas. But this is equal to the variance of x plus the square of the mean of x. The square of the mean of x. So ano yung variance ng x? Sigma square. Ito yon, sigma square. Ano yung square ng mean of x? Theta square. So we equate. We equate now. The sample moment x bar here, x bar here, equate natin yan sa first population moment, which is theta. Okay, so we have that. And then in this second one, itong second sample moment equal to the second population moment. So we have this. So solving for theta, obviously now theta hat, theta tilde rather. No, the theta tilde, it's the moment, method of moments estimator for theta, and that is equal to the sample mean x bar. And then sigma square tilde, ito yun, resulta niya. Because our theta here, itong theta natin dito, we replace that with the sample mean. So, i-transpose mo yan sa kabila. Ito, transpose mo dyan sa kabila. So, sigma square is this minus theta square. Okay, ito yung ngayon. So, yung theta square is sample mean square. We arrive at this. Madali naman yan. Pwedeng ganito yung pagka-simplify nyo. Yung x bar, square man yan. So, meron tayong sample mean pa dito. 1 over n, summation of xi. Okay, pwedeng ganun. And then we have 1 over n, summation of xi square. No, pwede. Labas natin yung 1 over n. Then we have here x bar, and then summation of xi. And then we can have 1 over n, the summation of xi square, minus 2 x bar xi. And then plus x bar xi, summation of xi. Okay, so pwede na yan. 1 over n. Kung ganun yan, then we have here, we can take that summation lahat. Lagay natin. So we have here, the summation of, say, xi square minus 2x bar plus x bar summation of xi. So pwede niya diretso. So we have that result. Xi minus x bar quantity square. Okay. So this is the method of moments estimator of theta equal to x bar. The method of moments estimator of the population variance, we have here sigma tilde square, so we have here. If we're going to look at this expression, hindi yan siya yung ating sample variance. Though by intuition, we usually want to estimate our mean by the population mean by the sample mean, and we're going to estimate our population variance by the sample variance. But in this case, hindi ito yung sample variance natin. Okay, so that's all. Lumampas ako ng 5 minutes. I'm sorry for that. So I'm going to stop now the recording. You just, ano tawag niyan?